Welcome to AI Paper Slop, the YouTube series where we summarize the latest AI and tech papers. Today we are looking at InstructSAM, segment any instance with any instructions. And this is by researchers from Zhejiang University and Nanjing University of Aeronautics and Astronautics.
Right, and if you're building in this space, here's the immediate TL. A DR InstructSAM essentially solves the problem of multi-instance segmentation when you have complex open-ended instructions.
Yeah.
So instead of relying on those, clunky agentic pipelines or a really slow autoregressive generation of segmentation tokens, they introduce this explicit reasoning to instance query interface.
Which is huge.
It is. It takes a 2 billion parameter vision language model, injects a bank of learnable instance queries into it, applies a hybrid attention mechanism, and then just projects those queries directly into the detector space of SAM3.
So the segment anything model.
Exactly.
Right.
And the result is you get this highly accurate multi-instance segmentation in a single forward pass. It completely eliminates the latency and instability that plague current methods.
And if you're an ML engineer or an AI researcher listening to this, the reason you should care is that it elegantly fixes this massive architectural bottleneck, right, between large language model reasoning and pixel-level grounding.
Right.
And it does all of this without modifying SAM3's core architecture whatsoever. Like, you get all the reasoning of an LLM paired with the pixel-perfect segmentation of SAM3, and it runs at hyper-efficient speeds.
Yeah. And to really appreciate the engineering here, we first need to dissect why that bottleneck even exists.
Right. We have to look at how current state-of-the-art models actually fail.
Exactly. So take SAM3 on its own. It's undeniably fantastic at concept-level prompting. Like, you give its prompt encoder a short noun phrase, something like traffic cone, and the mask decoder beautifully retrieves and segments multiple traffic cones in a scene.
But real-world deployment is, rarely that clean. When a human interacts with an embodied AI or some image editing tool, they don't just speak in isolated nouns.
No, of course not.
They use spatial relationships, negative constraints, contextual clues. They say, grab the Phillips head screwdriver that's underneath the red rag, but not the flat head.
Right, and that is exactly where the current paradigms just break down. The industry basically leans heavily on two fundamentally flawed workarounds right now for these implicit instructions.
Okay, so the first one being the agentic pipeline, right?
Yes, the agentic pipeline. In this setup, you take a frontier vision language model, say QuenVL or maybe Gemini, and you use it as a prompt rewriter. So you ask the LLM to translate that really complex instruction into a series of simple noun phrases.
Right.
Then you pass those isolated phrases to SAM3, which generates just a massive pile of candidate bounding boxes and masks. And then you have to use heuristics or another LLM pass to iteratively filter out the wrong ones.
Which honestly just sounds like a terrible game of telephone. You have this brilliant but completely blind manager, the LLM, trying to relay highly complex spatial logic to a really skilled but entirely literal worker, which is SAM3.
Yeah, that's a perfect analogy.
And every time they pass a message back and forth, all the nuance gets stripped away. Like, if you reduce the screwdriver under the red rag to just the noun screwdriver.
So SAM3 is going to segment every single screwdriver on the workbench.
Exactly. And then the filtering heuristic somehow has to reconstruct the spatial logic that was lost in translation. Not to mention, looping through an LLM and an image encoder multiple times. That's an absolute latency nightmare for any real-time application.
It's awful. It scales terribly in production, which is why a lot of researchers are pushed toward the second paradigm, which is the token as mask interface.
Right. You see this in models like Lisa or, say, 2VA or Lisa++ Mac.
Yeah. And the strategy here is to equip the multimodal LLM with a special segmentation token, usually formatted in brackets as SEG. So the model processes the image and the text, and when it wants to output a mask, it emits that seg token.
Got it.
And the hidden state of that specific token is then extracted and decoded directly into a segmentation mask.
But wait, semantic segmentation models use token emission all the time without issue, right? So if optimizing a model to emit a seg token works for pointing out a general semantic class like water or sky,
right?
Why does it fail so hard when we wanted to segment individual instances, like 5 distinct apples in a bowl? Can't we just let the autoregressive decoding run and spit out 5 seg tokens in a row?
You'd think so, but the failure there is structural. It's rooted in the nature of autoregressive text generation itself. The seg token is a shared universal symbol, right?
Right.
It doesn't have an explicit instance binding mechanism built into its architecture. So if you force a language model to spit out multiple seg tokens sequentially, like token update context, the latent space just often collapses.
Oh, wow.
Yeah, the model literally loses track of which specific instance it just mapped. So the resulting masks will often merge into identical duplicates, or the boundaries just become highly unstable.
Well, yeah, that makes total sense from an optimization standpoint. You're basically forcing a single overloaded symbol to represent 10 completely distinct spatial entities one after another.
Exactly. The attention gets completely diluted.
And frankly, autoregressive generation scales terribly with latency as the instance count grows. Like if you have a scene with 20 target objects, your model has to generate 20 sequential tokens running a full forward pass for the entire sequence each time before you can even begin decoding the first mask.
It creates a massive bottleneck. So if agentic loops lose semantic constraints, right, and autoregressive tokens suffer from gradient collapse and latency, how do we bridge the reasoning of the VLM and the spatial precision of SAM3 efficiently?
Right, which brings us to InstructSAM.
Exactly. This is where InstructSAM introduces its core innovation, which is the reasoning to instance query bank. They fundamentally changed the interface.
And this is the part of the architecture that really stands out to me. During the forward pass, when the language model's text generation hits a specific trigger token, the mask start token, it doesn't try to autoregressively predict the mask.
No, not at all.
Instead, it immediately inserts a bank of K learnable queries into the multimodal sequence, and by default, they set K to 10.
Right.
These queries just sit right alongside the visual tokens from the image encoder and the text embeddings from the prompt.
And this is huge because it changes the processing from sequential to parallel. Those 10 learnable queries are processed through the transformer layers simultaneously. The output is a set of contextualized hidden states, which the paper refers to mathematically as ZK.
Okay.
And each one of these queries basically transforms into a grounded instance hypothesis. It absorbs both the semantic intent from the instruction, so what we're looking for, and the localization cues from the image tokens, where it is in the scene.
So you completely replace a sequential one-by-one token generation with a parallel set-structured interface. So instead of sending one blindfolded scout into the woods, having him come back with a map, and then sending him out again 9 more times sequentially, you're dropping 10 independent, highly trained scouts into the woods at the exact same time, which is brilliant for latency.
It really is.
But, human nature and neural network optimization honestly tells me that if you drop 10 independent scouts into a scene and say, find the 3 red cars, they aren't going to divide the labor perfectly.
Right.
They're all going to just snap to the biggest, brightest red car in the foreground because that represents the path of least resistance for the loss function. So how does the model stop all 10 queries from just collapsing onto the exact same salient object?
That is the exact problem that requires their second major architectural innovation, which is their hybrid attention design.
Okay, how does that work?
Well, to prevent that mode collapse, you have to treat the text tokens and the mask queries fundamentally differently based on their roles in the sequence. So for the standard text tokens, InstructSAM uses standard causal attention.
Meaning the model can only look backward.
Right, which preserves the LLM's autoregressive reasoning capabilities. But the mask queries are granted full context bidirectional attention.
So to extend our scout metaphor, you didn't just drop 10 scouts into the woods. You gave all 10 of them open channel walkie-talkies.
Yes, perfect.
Because of that bidirectional attention, Scout 2 can actively see the attention map of Scout 1. So Scout 2 sees that Scout 1 has already localized heavily on the brightest red car in the foreground. Scout 2 actively suppresses its own activation in that region and pivots to look for the second red car in the background.
The walkie-talkie analogy is dead on. They can attend to the image, they can attend to the text, and crucially, they can attend to each other. This interquery communication is the exact mechanism that allows the model to capture set structure and actively suppress duplicate predictions, all in a single pass.
That is incredibly elegant engineering.
It really is.
So once these 10 queries have, negotiated with each other and localized their distinct targets, how do we actually bridge the gap into the segment anything model? Like, how do we get the actual pixel level masks?
Right, so they project those ZK embeddings directly into SAM3. The hidden states of the queries are passed through a lightweight multi-layer perceptron, an MLP, which acts as a translator, essentially mapping the VLM's latent space directly into SAM3's mask decoder space.
Okay.
Now, while this is happening, the language model also generates a very short, lightweight noun phrase, denoted as T-phrase, and this acts as auxiliary textual conditioning for SAM3.
I see.
From there, the SAM3 detector cross-attends the K-queries with the high-resolution image features. A score head predicts the validity of each query, basically asking, is this query tracking an actual object, or is it just an empty slot? And finally, the segmentation head outputs the binary masks.
Wait, okay, looking closely at that pipeline, I'm noticing a detail that feels a little bit like a cheat code.
Oh.
If the LLM is generating a short phrase, this T phrase, to pass into SAM3 alongside the queries, aren't we just sneaking an agentic pipeline back in through the back door? Like, is that text phrase actually doing all the heavy lifting for the segmentation while the fancy query bank is just along for the ride?
The researchers actually anticipated that exact skepticism, and the ablation studies in the paper definitively debunk it.
Oh, really?
Yeah. They tested exactly what happens if you sabotage that auxiliary phrase. If you replace the generated noun phrase with a dummy token, literally just padding it with token ID 0, the model's mean average precision barely drops at all. It stays highly accurate.
No way.
But if you remove the LLM conditioned query representations, those Zeek embeddings, and just rely on the text phrase, performance absolutely tanks.
Okay, so that's the smoking gun right there.
Yep.
The semantic power, the actual spatial reasoning and instance differentiation, is entirely housed within those bidirectional query embeddings. The text phrase isn't the engine, it's just like a tiny bit of scaffolding to help stabilize the SAM3 prompt interface.
Yeah.
The heavy lifting is done by the queries.
Correct. Now, you can design the most brilliant query interface in the world, but as anyone who builds machine learning models knows, an architecture is only as good as its supervision.
Right.
You cannot train a reasoning to instance model without data that explicitly maps complex implicit logic directly to specific instance masks.
And when you look at the landscape of open source data sets, that specific mapping simply didn't exist at the scale required.
No, it didn't.
Like you have data sets with billions of masks, but no complex reasoning.
Yeah.
Or you have data sets with complex reasoning, but no pixel-perfect instance masks. So the researchers had to build the fuel for their own engine.
They did.
They introduced a dataset called Inst2Seg. It contains 500,000 QA pairs for training, along with a highly rigorous benchmark of 3,328 manually verified instructions.
And the construction of that benchmark is vital because it spans single target scenarios, multi-target scenarios, and crucially no target scenarios.
Right, because teaching a vision model when not to segment anything is just as important as teaching it what to segment.
Exactly. It completely prevents the model from hallucinating objects that aren't actually in the scene just to satisfy the prompt.
I really appreciate the diversity of the source material they use to generate Inst2Seg 2. They use Gemini 3 Flash as the engine to generate the QA pairs, specifically prompting it to create hard negatives. You know, like asking for the apple that is half eaten next to the green bowl,
Right.
but ignoring the whole apples.
Right.
And to get the images, they pulled from standard giants like SA1B, which is the original segment, anything data set, obviously containing incredibly diverse scenes, and OCO 2017 for dense object interactions. But I think the smartest move was pulling heavily from egocentric data sets, specifically Ego4D and Epic Kitchens.
The inclusion of first-person egocentric data is a massive differentiator here.
Yep.
If you're training a model for real-world application like a robotic arm looking down at a cluttered kitchen counter, or maybe a wearable headset navigating a workshop, you're dealing with intense occlusion, weird angles, messy spatial relationships.
Right. Standard front-facing photography just doesn't prepare a model for that.
Not at all.
But looking at the data generation pipeline, the paper dedicates a lot of text to a specific, highly stringent filtering stage after Gemini 3 Flash generated the QA pairs.
Yes, it does.
Given that Gemini is a frontier, state-of-the-art model, why go through the massive compute overhead of filtering its output? Shouldn't a model of that caliber give us clean spatial data right out of the box?
You'd hope so, but the engineering reality is that naive generation from frontier vision language models is absolutely packed with label noise, particularly regarding spatial logic.
Oh, interesting.
Yeah, LLMs hallucinate spatial relations constantly. The text might say the mug to the left of the laptop, but it will link that text to the bounding box of the mug on the right. And if you train a pixel-level model on that misaligned data, you're actively teaching it to be stupid. The ablation metric they provide on this is staggering.
What was it?
When they trained InstructSAM on the Inst2Seg data without that filtering stage, the mean average precision, or MAP, dropped from 31.5 down to an abysmal 11.9.
Wow. A drop from 31.5 to 11.9 is catastrophic. It basically means the model went from state-of-the-art to just guessing.
Exactly. High quality, perfectly aligned supervision is completely non-negotiable for this architecture. To get the model to actually learn the query interface, they had to utilize a strict two-stage training process.
Okay, walk me through that.
So stage 1 was a referring alignment stage. They froze most of the LLM and just used 2.5 million simple single-target samples to teach the new learnable query space how to essentially talk to SAM3.
Got it. Just getting the translation layer stable.
Right. And once that was stable, stage 2 was the actual reasoning instruction injection, where they unfroze the model and trained it on the complex, filtered Inst2Seg Dataset to teach it the compositional logic.
Okay, so we have an elegant parallel query architecture, and we have the high-quality, heavily filtered data to fuel it. How does this model actually stack up against the heavyweights? Because keep in mind, InstructSAM is built on the Qwen3VL backbone, which is a 2 billion parameter model.
Yeah, which is tiny.
Right. In the era of massive foundation models, 2 billion parameters is practically small enough to run on your phone. So how does it compete?
It absolutely crushes prior end-to-end methods across every meaningful metric.
Really?
Yeah. On their newly established Inst2Seg benchmark, which tests that implicit multi-target reasoning, InstructSAM hits that 31.5 MAP. The next best performing model is XSAM, which is nearly double the size at 3.8 billion parameters, and it only manages an 11.0 MAP.
That is wild.
It significantly outperforms LASA, it beats PixelM, and it even outperforms the 8 billion parameter version of SA2VA.
Beating an 8 billion parameter model with a 2 billion parameter model purely by optimizing the query interface and eliminating autoregressive collapse is incredible. It proves that scaling parameters just isn't the only way to solve complex reasoning, you know? Sometimes you just need a better data structure.
Exactly. And the dominance extends to legacy benchmarks as well. On the established GraphCoco benchmark, it achieves a semantic CIOU of 68.3.
And for context for you listening, CIOU stands for Complete Intersection Over Union. So it's a metric that measures not just if the model found the object, but how perfectly the predicted mask boundaries overlap with the actual ground truth object boundaries.
Right. And a score of 68.3 on complex referring expressions is exceptional. It also tops the charts on GSEVol.
Yeah.
But the most telling result, I think, is its performance on Robotics.
Oh, Robotics. That's the robotics visual grounding benchmark, right? For anyone working in embodied AI, that is essentially the ultimate stress test.
It really is.
Because it's not just internet photos. It requires localizing target objects based on language commands in messy, real-world indoor environments.
Exactly. And on Robotics, InstructSAM beats previous task-specific segmentation models by a massive positive 12.9 margin on the distribution-shifted test B split.
Wow.
And that split specifically tests the model on environments and object compositions it hasn't seen before. That plus 12.9 margin proves that InstructSAM isn't just memorizing its training data, right? It has actually learned the underlying implicit spatial logic and can generalize that logic to entirely novel environments.
And we know exactly which parts of the architecture are driving that success, too, because the researchers did a fantastic job with their ablation studies.
Oh, absolutely.
We already mentioned the text phrase ablation, but if you remove the query bank entirely and force the model back into autoregressive token generation, that Inst2Seg MAP drops from 31.5 back down to 20.1.
Yeah.
And if you keep the queries but remove the hybrid attention, meaning you take away the walkie-talkies and the queries can no longer talk to each other to suppress duplicates, performance on the ReasonSeg benchmark drops from 65.0 down to 52.4. So every single piece of this architecture is load-bearing.
The system really requires all of its parts to function optimally. But there is one final ablation regarding scaling that reveals a very interesting property of this set prediction structure.
Oh, you're talking about the query parameter, K.
Yes.
By default, they drop 10 learnable queries into the sequence. The immediate engineering instinct is, if 10 parallel queries give us a 31.5 MAP, why not just throw compute at the problem and send in 200 queries? Like cover every possible square inch of the image.
Right. Which they actually tested, increasing K from 10 to 200.
In doing that, obviously doubles the inference time, pushing it from 1.1 seconds to 2.1 seconds. But fascinatingly, it actually decreases the MAP slightly, dropping it from 31.5 down to 31.1.
Yeah, and the data backs up a fundamental limitation of attention mechanisms here. The efficiency of a set prediction structure maximizes at a relatively small number of slots.
Makes sense.
If you flood the transformer with 200 queries that all have full bidirectional attention, the interquery communication just becomes way too noisy. The queries start picking up redundant signals, the attention maps dilute, and the MLP basically struggles to project clear, distinct object hypotheses into SAM3.
Right.
So setting k equal to 10 is this optimal, hyper-efficient sweet spot where the queries can negotiate distinct targets without drowning each other out. You really don't need a massive query bank to get perfect scene segmentation.
It is just a masterclass in elegant engineering. So to summarize the core takeaways for everyone tuning into AI paper slop, InstructSAM successfully escapes the trap of autoregressive mask generation and those brittle, error-prone agentic pipelines. By using parallel cross-attending instance queries, a highly efficient 2 billion parameter language model can effectively pilot the massive SAM3 engine in a single coherent forward pass.
Exactly.
It bridges the massive gap between complex human reasoning and pixel-perfect segmentation, all without sacrificing latency.
Right. And before you close out your notes, I do want to leave you with one final thought regarding the broader implications of this architecture.
Oh, please do.
If a relatively small 2 billion parameter model can translate highly complex implicit reasoning into pixel-perfect, multi-instant set predictions simply by reshaping the query interface and utilizing hybrid attention, what happens when we apply this exact parallel query paradigm to other critical bottlenecks in the field? Could this bidirectional query interface be the missing key to achieving continuous, fluid robotic control in embodied AI? Or perhaps could this parallel set prediction structure solve the temporal consistency problems currently plaguing real-time video generation? The implications here go far, far beyond just segmentation.